So today we are going to start our lectures on steady state sinusoidal circuit analysis by effectively setting up the ground rules. And to that end, the first topic we are going to talk about is what I'm calling forced response. Due to sinusoidal inputs. So as a very brief recap of what the concept of forced response means, we're going to analyze a trivial circuit. So let's say that I have some DC voltage source supplying some voltage Vs to the following network containing a resistor R and an inductor L. That voltage source Vs is what is called a forcing function because it is applying external excitation to the system and generating a specific response. So for example, our responses of interest could be the voltage drop over the resistor, VR, the voltage drop over the inductor, VL, or the current flowing through the network. In each of these cases, we observe that when we apply a DC forcing function, all three of those possible responses are also DC quantities. So for example, we know that VR should just be exactly equal to Vs in this case. As we analyze this guy as a DC circuit, we would know that VL must be equal to 0 volts if we analyze this guy as a DC circuit. And finally, we would know that I would have to be Vs over R. Again, all three possible responses are DC quantities due to the fact that we are exciting this guy with a DC forcing function. So we're going to take this exact same simple circuit and analyze it in the time domain with sinusoids and break things. All right. So if we have the same circuit, but now my source voltage will be time varying. Sorry, that should be VR. Where Vs of t will have some value. I'm going to call it Vs naught cosine omega t plus theta Vs. So we have a sinusoidal forcing function that has some particular amplitude, Vs naught, a particular excitation frequency, omega, and a particular phase angle. So let me be explicit about what these things are. So this guy right here is our amplitude, omega, our angular excitation frequency, and theta Vs is our phase angle. if we were trying to determine the current that flows in the circuit in particular, I of t, I would argue that our expectation of how I of t is going to behave will be that it is also going to be a sinusoidal function. Having some particular amplitude, frequency, and phase angle. The frequencies will be identical, but the amplitude and the phase angles will not be. Okay? So, kind of relationships here. So if we applied Kirchhoff's voltage law, we would find that V of t will be equal to, Vs of t will be equal to Vr of t plus VL of t, which we could also express as R times I of t plus L di by dt. So what we are about to do is effectively figure out how this amplitude I naught and this phase angle theta I depend on the values of the amplitude and phase angle of the voltage, as well as the resistor value and the inductor value, right? We want to know what the relationship between those things are. So we're effectively trying to suss our way through a current voltage relationship like we've been doing with everything else. All right, so again, laying the ground rules for our, whatchamacallit here, circuit analysis. So what I am going to do is I'm going to apply a particular trig identity to my current waveform here. So the trig identity that I'm going to apply, I'm going to put it in a box, is cosine omega t plus, I might even do it like that. Cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. So if I apply this trig identity, what I get, sorry, that should be black, is pen thing, Vs naught cosine omega t. I am intentionally assuming a phase angle of 0 for my voltage signal here. Okay, so I'm going to explicitly say let theta Vs equal to 0 degrees just to make the math easier, or slightly less difficult to follow, really. All right. So Vs not cosine omega t will be equal to R multiplied by, and now I'm applying this trig identity. So if I have a constant term out front, that same constant term is going to be multiplied through by this guy. So that should look like I naught. I'm going to say that alpha is omega t, because that just represents an angle, right? Omega, which is measured in radians per second multiplied by time, just gives me an angle. And obviously beta is then going to be theta I, which is just another angle. So I'm going to have I naught cosine, oh sorry, cosine omega t cosine theta I minus I naught cosine omega t cosine theta I. You're right, sorry. Brain fart there. Thank you. Because otherwise that would just give me 0. Thank you for catching that. I would have greatly confused myself. Minus L times the derivative of I naught cosine omega t cosine theta I minus I naught sine omega t sine theta I. I'm going to make another simplification here real quick. I am going to say I naught is just a number, right? It is a magnitude. Okay, so it's going to have some specific value. And cosine of theta I is also going to have some specific value, because theta I is going to be a constant number. And so when I take the cosine of that constant angle, I get a constant value. So I can combine I naught cosine I and I naught sine I and replace them with just another variable that represents a constant. So as a quick aside here, I'm going to explicitly state that I'm going to call A1 is going to be I naught cosine theta I. A2, I will say, is negative I naught sine theta I. This allows me to rewrite this guy as R times A1 cosine omega t plus A2 sine omega t sorry, that should have a plus on here, plus L d by dt, that same expression, A1 cosine omega t plus A2 sine omega t. Now I'm going to do the indicated derivative. And so this is going to give me, I'm going to have R A1 cosine omega t plus R, bless you, A2 sine omega t plus omega L A1. So let's see here actually. So when I take the derivative of cosine with respect to time, that's going to be negative sine, right? And then because it's cosine omega t, it should be negative omega sine. So let's see, negative omega L A1 sine omega t. When I take the derivative of the sine function, that's going to be omega, positive omega cosine. So that should be plus omega L A2 cosine omega t. If I did my calculus correctly, and I think I did. So omega L A2 cosine, yeah. All right, and so what I can do now is just kind of group like things together. So for example, I have R times A1 plus omega L times A2. All of that gets multiplied by cosine omega t. And I have R times A2 minus omega L A1 times sine omega t. And just to be clear here, out here I have Vs naught cosine omega t. Okay, so I can easily see that R times A1 plus omega L times A2 has to be equal to the quantity Vs naught, my amplitude of my voltage waveform. The reason I say that I can see that easily is because on the left-hand side, I have some constant term multiplied by cosine omega t. And on the right-hand side, I have some constant term multiplied by cosine omega t. So I'm simply equating the amplitudes, right? Nothing wild or crazy there. And I can also see then that R times A2 minus omega L times A1 must be 0, because on the left-hand side, I have 0 times sine omega t has to be equal to the constant times sine omega t on the right-hand side. All right. So I have two equations with two unknowns. And so I can solve this system to determine what A1 and A2 are in terms of Vs naught, R, omega, and L. And so when I solve these guys, what I find is that A1 is equal to R times Vs naught divided by R squared plus omega squared L squared. And A2 is equal to omega L Vs naught divided by that same denominator, R squared plus omega squared L squared. From which we can say I of t will be equal to, so up here, let's see, I'm trying to think of how to, so we get to this trig identity thing here, right? A1 cosine omega t plus A2 sine omega t that is representative of our current response, right? We did a trig identity to kind of FOIL it out, and then we put in these two guys right here because we know that they're constants, allowing us to express I of t as simply A1 cosine omega t plus A2 sine omega t, which would give us R times Vs naught divided by R squared plus omega squared L squared times the cosine of omega t plus omega L over Vs naught divided by R squared plus omega squared L squared times the sine of omega t. So we have, in some shape or form, related our current response equation to the parameters of the circuit, right? The value of the resistor, the value of the inductor, and the amplitude of the voltage. That being said, this form, the sum of sinusoids, is not our expected response equation, right? So, excuse me, what I mean by that is we are expecting it to be a single sinusoid with a phase angle. So now we have to figure out how to get back to that form. So, excuse me. We can say, note up here, I have A1 is equal to I naught times cosine theta I, and A2 is equal to negative I naught times sine theta I. So I can use these relationships, right? So I can say that so A1 we know to be I naught cosine theta I, and it is also equal to R times Vs naught over R squared plus omega squared L squared. Similarly, A2 is equal to negative I naught sine theta I is equal to omega L Vs naught over R squared plus omega squared L squared. And so I'm going to do a little bit of change here, and I can say that I naught sine theta I then must be equal to negative. My pen thing will write omega L Vs naught divided by R squared plus omega squared L squared. Okay, so I'm about to bust out a couple of more pretty easy trig identities. For example, I could say that I naught cosine theta I squared plus I naught sine theta I squared would be equal to I naught squared times cosine squared theta I plus sine squared theta I, which is then simply I naught squared, right? Because we know that cosine squared x plus sine squared x is equal to 1 by definition. So this allows me, using this simple trig identity, allows me to determine what the amplitude of my waveform should be. So from this, I can see that I naught squared is effectively just A1 squared. So that would be R times Vs naught divided by R squared plus omega squared L squared, quantity squared, plus negative omega L Vs naught divided by R squared plus omega squared L squared, quantity squared. So that's going to be R squared Vs naught squared over R squared plus omega squared L squared, quantity squared, plus omega squared L squared Vs naught squared divided by R squared plus omega squared L squared, quantity squared. Looks like R squared plus omega squared L squared multiplied by Vs naught squared divided by R squared plus omega squared L squared, quantity squared, which is the same as Vs naught squared divided by R squared plus omega squared L squared. You follow my algebra there. So I squared everything as I was supposed to do. I grouped like terms and see that I have a factor in the numerator that is the same as the factor in the denominator, except the denominator is squared. Cancel those guys out. And finally, this yields I naught must be the square root of this result. So that would be Vs naught divided by the square root of R squared plus omega squared L squared. So we know what our magnitude is related to the parameters of the circuit: frequency, value of the resistor, value of the inductor, amplitude of the voltage. Now let's talk about how we get our phase angle. Well, by definition, the tangent theta I will be the sine of theta I divided by the cosine of theta I, right? Now we don't know technically the sine or the cosine. What we know is I naught times the sine and I naught times the cosine, but conveniently those I naughts cancel each other out, right? So I naught sine theta I is going to be negative omega L Vs naught divided by R squared plus omega squared L squared. We knew that from before. And I naught cosine I is R times Vs naught divided by R squared plus omega squared L squared. Since both of these fractions have a common denominator, they cancel out. leaving us with negative omega L over R, from which we can say theta I is the inverse tangent of negative omega L over R, or negative the inverse tangent of positive omega L over R. So putting these results together, I of t then becomes Vs naught divided by square root of R squared plus omega squared L squared cosine omega t minus the inverse tangent of omega L over R. So we finally have this guy in our expected form. And it only took us half an hour. Now, this was analyzing the circuit entirely in the time domain, right? And applying multiple trig identity. Well, actually, for the most part, it's really just that one trig identity that I circled that you guys might not be super familiar with. And then the sine squared plus cosine squared is equal to 1 trig identity, and literally the definition of the tangent function as the sine of an angle over the cosine of an angle. So it's not a ton of trig identities, but it's enough to be disturbing. If, so the analysis that we did is valid for this 3-element circuit. So if I put a resistor R2 here, it would literally break all of the work that we have done. We would have to completely and utterly reanalyze it and all that kind of stuff. So obviously, this is untenable. Like, we cannot do this in perpetuity because it'll take us 5 hours to analyze a trivial circuit that we were able to do in circuits 1 or whatever with, having just a few circuit elements would make these things just ungodly hard to analyze. So we are going to take a slightly different approach. All right, so how many of you are familiar with Euler's identity? Okay, so Euler's identity. Euler's identity says, there's a couple of different ways to write it. I'm going to write down the way that we're going to use it, and I'm going to write down another way just because I really like it. So Euler's identity says that cosine of, actually, let me write it the other way around. E to the j theta, where theta here is just a generic angle, is equal to cosine theta plus j sine theta. All right. So we could say then, using Euler's identity, that e to the j omega t, excuse me, e to the j omega t plus some phase angle phi is then cosine omega t plus some phase angle phi plus j sine omega t plus some phase angle phi. Okay. That's the one that we are going to be using in a moment. But another expression of Euler's identity that I think is absolutely amazing is e to the j pi plus 1 is equal to 0. We're never going to use that in this class. I just love this thing. Like if I were to ever get a tattoo, it would be that. And the reason why, if we look at this thing, it's bananas. The irrational number e raised to the imaginary power of pi plus the number 1 is equal to 0. So it relates all of the effective fundamental truths of mathematics. You know, pi, e, the concept of imaginary numbers, the number 1, unity, and 0 are all boiled together in one nice, beautiful equation. So anyway, this is a math nerd's wet dream. All right, that was inappropriate. I apologize. Okay, so Euler's identity. Let's circle back around to what we've got here on the left-hand side. All right, so we know from our understanding of complex numbers that they have a real part and an imaginary part, right? Where this guy right here is the real part of e to the j omega t plus phi. And this guy right here, everything multiplied by the j, is the imaginary part of e to the j omega t plus phi, right? So we could then argue that Vs naught cosine omega t is simply the real part of Vs naught e to the j omega t. And similarly, I naught cosine omega t plus theta I is simply the real part of I naught e to the j omega t plus theta I. So what this will allow us to do is analyze the circuit using complex numbers. But let me explain exactly why that works, all right? Let's say that we have a black box network, like so. Where on this side, we apply Vs naught cosine omega t. That is our input. I'm going to call it x1 of t. We observed a response. I'm going to call it y1 of t. That was I naught cosine omega t plus theta I, right? That's the expected result. So it's of the same form, but it'll have a different amplitude and potentially a different phase angle, okay? So that's our black box network representing any simple circuit containing only resistors, capacitors, and inductors whose parameters do not vary with time. Now let me ask you guys a question. Let's say I apply a different input, slightly different, x2 of t, where this were Vs naught sine omega t. What would you expect our output or response to be? So the only thing that we've done is we have effectively shifted our input signal by 90 degrees. Another way to think about it is that we started measuring it at a different point in time. What's going to happen to our output? It's going to be a sine. Yeah, everything is going to be exactly identical, except that if we put a sine in, we get a sine out. I naught sine omega t plus theta I. All right, so do any of you remember the homogeneity or scaling property of linearity from circuits 1? What did it say? Ballpark it, if you remember it. Exactly right. So we can multiply the input by a parameter or a time invariant constant. If we multiply the input by some time invariant constant, we also multiply the output by that same time invariant constant. So what I'm going to do is I'm going to say that there is a time invariant constant of j multiplying the input, giving me a multiple of j at the output as well. And so now I'm going to apply the additivity principle of linearity, which you guys probably know better as the superposition principle. That says I apply both inputs, x1 and x2 simultaneously. So if I have x1 of t plus x2 of t, which would be the same as Vs naught e to the j omega t, my response will be y1 plus y2, which would be I naught cosine omega t plus theta I plus j I naught sine omega t plus theta I. And I'm intentionally leaving it in this form, although I could just as easily combine this into a complex number. So what is incredibly interesting about this is that based on our experience of working our way through these things, the real part of the output is due entirely to the real part of the input, and the imaginary part of the output is due entirely to the imaginary part of the input. What that means is that if we analyze a circuit using a complex representation of our voltage and a complex representation of our current, we can get the exact same answer that we would have gotten by analyzing it with a sinusoidal signal for our input and expecting to get a sinusoidal signal as our output, but we get to use complex math, which turn out will be much easier to do. So let me explain All right, we're going to analyze that exact same circuit again. Here's Vs of t. Here's R. Here's L. And our goal is to figure out what I of t is, recognizing that if we have Vs of t is equal to Vs naught e to the j omega t, then we should see that I of t will be I naught e to the j omega t plus theta I, where my expectation is that I naught will be the same as our sinusoidal relationship, and our phase angle will also give us the exact same answer that we got when we analyzed the circuit using the sinusoidal relationships with all the trig identities and stuff. So, applying KVL, we get Vs of t, so that would be Vs naught e to the j omega t is equal to R times I of t, so that's R times I naught e to the j omega t plus theta I plus L d by dt times I naught e to the j omega t plus theta I. I'm going to do my derivative. So this is going to give me, I'm actually going to do two steps here. I'm going to do my derivative, but I'm also going to split my current exponential up. And so what I mean by that is e to the j times omega t plus theta I is the same as e to the j omega t multiplied by e to the j theta I. So I naught e to the j omega t e to the j theta I. Everybody understand how that product of two exponential functions is the same as the thing above? Okay. All right, so if I do that form, it's actually much easier to take the derivative as well, right? So when I take the derivative, what's going to happen?
The j will come out in front, and it will be e to the j omega t.
Yep. So I will have j omega L, and then I naught e to the j omega t e to the j theta I. So on both sides of the equal sign, I have a common factor of e to the j omega t that's showing up everywhere. So I can just cancel that guy out. So that leaves me with Vs naught is equal to R times I naught e to the j theta I plus j omega L times I naught e to the j theta I. And I'm going to group terms here, leaving me with R plus j omega I, or excuse me, omega L times I naught e to the j theta I. And finally, I'm going to divide So Vs naught divided by R plus J omega L will be equal to I naught e to the j theta I. Okay. So this is our intermediate point here. Kind of the same in as much as when we had the sum of sinusoids and how to get it back to that original form. This is our similar spot here, but we've done significantly less work to get to that intermediate spot. So let's take a moment and look at what we have here. On the left-hand side, we have a rectangular form complex number, or at least we have a rectangular form complex number in the denominator. And on the right-hand side, we have a polar form or exponential form complex number. And we know that there is equivalency between those two forms, meaning that there's a pretty easy way to relate everything that we have on the left to the magnitude of what we have on the right. And there's a pretty easy way to relate everything that we have on the left to the phase angle of what we have on the right, right? So just as a brief recap, if I have a complex number, A is equal to A plus JB, which is also equal to the magnitude of A, E to the J theta A, go away thing, right? I'm saying that these two numbers are equal. I can say, stop pulling up weird windows. The magnitude of A is equal to the square root of the real part squared plus the imaginary part squared. And my phase angle, theta A, is simply the inverse tangent of the imaginary part divided by the real part. So what we need to do now is to figure out how to split the left-hand side into its real and imaginary portions. And then we can directly apply both of these rules to figure out what the magnitude and what the phase angle is. So any thoughts on how we effectively get rid of the complex number in the denominator to create a complex number in the numerator with a real denominator? Any thoughts? That is definitely part of it. So when we multiply that complex number by its conjugate, if we do that by itself, okay, yeah, so we'll multiply the top and bottom by the conjugate of the denominator, okay? So that would be, actually, it doesn't need to be that large. Vs naught divided by R plus J omega L. How do I take the complex conjugate? Change the sign on the J term. Absolutely right. So that'll be R minus J omega L, and then R minus J omega L goes here. This is going to give me Vs naught times R minus J omega L divided by R squared plus omega squared L squared. And I'm just going to split things up here real quick. So that's going to give me R times Vs naught divided by R squared plus omega squared L squared minus J omega L Vs naught divided by R squared plus omega squared L squared. And now I can easily determine both the magnitude and the phase angle. So our magnitude I naught will be square root of the real part squared. So that's R VS naught divided by R squared plus omega squared L squared. This whole thing squared plus the square of the imaginary part. So that is negative omega L VS naught over R squared plus omega squared L squared, quantity squared, will be R squared VS naught squared plus omega squared L squared VS naught squared divided by R squared plus omega squared L squared, quantity squared. And I can group terms together, leaving me with VS naught squared times R squared plus omega squared L squared divided by R squared plus omega squared L squared, quantity squared, finally giving me VS naught divided by square root of R squared plus omega squared L squared. So our magnitude, with, in my opinion, considerably less work than we had to do previously, gives us the exact same result as we had. Our phase angle will be the inverse tangent of negative omega L VS naught divided by R squared plus omega squared L squared divided by the real part, R VS naught over R squared plus omega squared L squared. And so we have a common denominator that cancels each other out, and we also have a common factor of VS naught in each of the numerators, leaving us with the inverse tangent of negative omega L over R, which is the same as negative the inverse tangent omega L over R, which is also the exact same result we got previously. So using the complex number method got us our answer in, I would consider, a considerably less amount of math. All right, so it was less math, but it was still too much math. All right. So now we are going to start by introducing the electrical engineer's shorthand notation for these signals, right? Phasors. So generically, let's say that we have a signal V of t is equal to Vm cosine omega t plus theta v, and a current signal it is equal to Im cosine omega t plus theta I. These guys represent our time domain representation of those sinusoidal signals. Well, we know that V of t is simply the real part of Vm e to the j omega t plus theta v, and I of t is simply the real part of Im e to the j omega t plus theta I. I'm going to call this the mixed domain, which is what we just worked in. So what electrical engineers have done is they've gotten lazy. Most of our innovations are driven by laziness or the not wanting to do a particular thing, all right? So electrical engineers have come up with a shorthand notation that represents that same time domain signal as a complex number. I'm going to call it V. My voltage phasor is simply Vm with an angle theta V. And I'm going to represent my phasor current I bar as Im angle theta I. So this is really the same thing as our mixed domain relationships, except that we are throwing away the frequency characteristic with the understanding that we know that that frequency characteristic is constant among all of the terms, which is exactly what we saw in our last circuit analysis, right? We had a constant term of e to the j omega t that showed up in everything. So if it shows up everywhere, we can just cancel it out, and that leaves us with our phasor representations. All right. So I think this is a good stopping point for today, introducing phasor voltage and phasor current. What we are going to do on class Thursday is use these phasor relationships to develop frequency domain relationships for all of our circuit elements so that we can get into full-on frequency domain circuit analysis where all of that terrible calculus that we did in the time domain becomes algebra due to phasors. All right, so I don't know why this is oddly. All right, any questions? So this was all a whole bunch of setup to get us to appreciating complex numbers effectively, showing you how terrifying it is to work in the time domain.